Hello everyone, in this video we will going to discuss about memory management from operating system. In memory management we will discuss about background, swapping, contiguous memory allocation, segmentation, paging, structure of the page table. Background. Program must be brought from the disk into memory and placed within a process for it to be run on the CPU. Every program needs to be in the ready queue for the execution purpose. So here main memory comes into existence, and main memory and registers are only storage in the CPU. The CPU can access directly. It cannot directly access from hard disk or backing store. It only access the process from main memory and register, because register access in one clock or one CPU clock, and main memory can take many cycles just because main memory is in less capacity than the hard disk. And cache sits between main memory and CPU. Cache lying between the main memory and CPU registers, and protection of memory required to ensure correct operation. For this all purpose, memory management is required from the operating system. Here comes the existence of base and limit register. There are two registers, that is called base register and limit register. A pair of base and limit register define the logical address space. CPU first check every memory access generated in user mode to be sure it is between base and limit for this user. So every time when program is generated, program generates a logical address. That logical address should be when it is to be taken into main memory, it must be ensure that the size of the process should be within the limit register, whatever the size of the limit register, the process size should satisfy that size. Otherwise the process cannot be taken into the memory. And base register kept the first address which is free in the main memory, first block of address which is free. So these are the two register which is required for memory management. We can see here that the base register kept 3 0 0 0 40. That means the address from 3 0 0 0 40 is free to occupy any process. And the limit register 1 2 0 9 0 0 means any process which is coming within this size, the size from 3 0 0 40 to 4 2 0 9 40 means the size of the any process should be within this limit register. We can see here the hardware support from operating system, hardware address protection, where base and limit register have some role. And we can see that through CPU program generates some address, and we first check that the address should be starts from the base register, where base register is the first address, free address, where we can from where we can keep the process. And it should be the address which is generated should be greater than or equal to the base register. If it is yes, then we can proceed further. After that we check the second thing, whether the size of the process is less than the limit register. So we can check that the size of the process should be the base address starts where the base the space starts, and the size of the block, free block, the sum of that base and limit should be the less than the size of the process, size of the address which is generated by the CPU. If it is okay, if it is yes, the condition is yes, then the process should be kept into the memory. Otherwise the addressing error is given by the operating system. Binding of instruction data to memory. Address binding is basically bind the process into memory, and this binding can be categorized into three types: compile time binding, load time binding, and execution time binding. Compile time binding, we can say if memory location known in advance, then absolute code be generated. Whatever the code is generated, the process is as kept as it is into the memory. That is basically compile time, and this is called absolute code, and it can be generated, and it must be recompiled code if starting location changes. So whenever the location is changed, if there is any changes in location, then the program should again be compiled. So recompilation will be required to generate absolute code. Then load time binding, it must generate a relocatable code. Means we can generate such kind of code that can be relocated when the address is changed. Relocatable code can be generated, and memory location is not known at compile time, then it is called load time binding. Execution time, when binding delayed until runtime, when the process runs or executes, till then the binding is delayed. So it is called as binding delayed until runtime if the process can be moved during its execution from one memory segment to another. So execution time, when it is required to shift one program or process from one memory location to another memory location, then this time of binding is called execution time binding. Now we can discuss about logical versus physical address space. So the concept of logical address space, that is bound to separate physical address space and central to proper memory management, and the logical address is generated by the CPU, and that is also called virtual addresses. So CPU generates logical address, and this is the program address. Physical address seen by the memory unit. When this program is converted into process and we keep that process into main memory, then that address is called as physical address. So logical address is the set of all logical addresses generated by a program, and physical address space is the set of all physical addresses generated by a program. Dynamic relocation using relocation register. So we relocate according to the base and base register and limit register, and then we can relocate um, dynamically the process into the memory through, and that can be done through relocation register. So one of the memory management is called swapping, and what we do in swapping, we only take those part of process or those programs which is required, and after completion of that process, we again keep it back to the hard disk. So that process is known as swapping. So a process can be swapped temporarily out of memory to a backing store and then brought back into memory for continued execution. When it is not required, then temporarily it is taken off from the memory and kept into the backing store. Basically, backing store is our hard disk. Backing store is basically hard disk large enough to accommodate copies of all memory images for all users must provide direct access to these memory images. Roll in. What is this? Swapping variant used for priority based scheduling algorithm. Lower priority process swapped out, so higher priority process can be loaded and executed. So when there is some higher priority process comes, the lower priority process is swapped back or rolled back from main memory to the hard disk, and higher priority process is allotted to the CPU for execution, that is roll-in. So major part of swap time is transfer time, when we swap in and swap out or roll in and roll out so many time. So the swap time is bigger than the execution time. So most of the time gone for swapping only. So major part of that time is transfer time, transferring the process from main memory to hard disk to main memory. System maintains a ready queue for ready to run processes which is have memory images on disk. So ready queue is basically kept in memory, and it is nothing but it is the queue of process, and which is kept in memory whenever a process comes into the main memory. for execution. We can see here a schematic view of sapping. There is a main memory given this side, and backing store is this side. So whenever a process is required, it is it is taken from the backing store to the main memory, and whenever the process completes its execution or due to some interrupt, we keep this process and swap out this process from main memory to backing store. Now, what is contiguous allocation? Main memory must support both operating system and user processes. Limited resources must allocate efficiently. Contiguous allocation is one early method. Main memory usually into two partition. Resident operating system usually held in low memory with interrupt vector. User process then held in higher memory. Each process contains a single continuous section of memory. So whenever any process comes, all the process are kept in one place in contiguous memory location. That is basically called contiguous allocation. And in general, the whole operating system is kept in one side of memory, that is lower part, and the rest of the part is available for the user processes. And here we can see the hardware, how hardware support the relocation and limit register for process, which we have discussed earlier already. Multiple partition allocation. In multiple partition allocation, that is also called MFT, multi-programming is a fixed number of tasks. So we have multiple partition, but which is fixed initially, or number of process or programming is fixed. Suppose we have six partition in the memory, so we can have at most six process at the time. So degree of multi-programming become six. We can see here is the diagram. There are three partition except operating system. There are four partition including operating system. But operating system, besides operating system, there are only three parts, and only three parts is there. So we can have three program at a time, three process at a time in memory. So degree of multi-programming becomes three. So degree of multi-programming limited to the number of partitions, and variable partition sizes, in which we have fixed number of partition, but the size may vary. The size of the partitions are different. And whole is a block of available memory. Holes of various size are scattered throughout memory. When a process arrives, it is allocated memory from a hole large enough to accommodate it. So if they suppose we have a process number 8, so process number 8 is occupied in the given blue area, because the process 8 is size of the process 8 is equal to that block only. And like that, process 5 is kept into the into that size, which is sufficiently available for sufficient for the process number 5. And when process exiting freeze its partition, adjacent free partition combined. So in this particular case, when the any process exit from the memory, then the process that partition is available for the another process. Operating system maintains information like allocated partition and free partition, so that in next time when any process comes, it can occupy that that process.